Welcome to the Problemas channel season 2 episode 34, the episode which I titled a 3x3 magic square construction, because in this episode we will use the eliminate and conquer problem solving approach in order to construct a sample 3x3 magic square. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailers section, find the episode titled The Problemas Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. The challenge in the mathematical problem S2E34 is to fill out a 3x3 magic square with a constant of 15 using precisely the eliminate and conquer problem solving approach. And yes, in season 2 episode 29 we discussed and explained how the so-called Bechet algorithm works, and that is a wonderful algorithm that allows us to pretty much mechanically and thoughtlessly to construct any magic square whose order is an odd number, and the order of a magic square is basically its linear size. For example, in our case, the linear size of the square is 3 columns wide and 3 rows tall, 3 by 3. Consequently, the order of this magic square is 3. 3 is an odd number, and in theory, yes, we can apply the Bechet algorithm to, again, mechanically and thoughtlessly fill out this 3 by 3 magic square, call it a day, and move on with our lives. However, that is not the objective of the mathematical problem S2E34. The objective of the mathematical problem S2E34 is to precisely apply the eliminate and conquer problem solving approach to the process of solving this problem S2E34, and to work one more time on the mechanics of the application of the eliminate and conquer problem solving approach to the process of obtaining a solution of this or that technical problem. In other words, for the duration of the solution of the mathematical problem S2E34, we will pretend that we do not know anything about the existence of the algorithm due to Bechet, and we want to hear the story or a story behind how we can fill out a 3 by 3 magic square with a constant 15, not in a haphazard way, hoping to get lucky and hoping that somehow and eventually things will work out, but in a way that has some mathematical sanity behind it. And in this episode, we will do precisely that. We will see how the eliminate and conquer problem solving approach can be used in order to fill out a 3 by 3 magic square with a constant of 15. Very good. In season 2 episode 29, one more time I will refer to this episode. If you for some reason missed this episode and did not watch it, then we recommend probably a good idea for you to go find that episode and watch this episode in its entirety. But in this episode we covered the fundamentals of a magic square. If you do not know anything about magic squares, then you already know one thing. You know what the order of a magic square is, and the order of any magic square is its linear size. If the magic square is 3 by 3, then its order is 3. If the magic square is 4 by 4, then its order is 4, and so on. Also, in season 2 episode 29, we discussed the fact that the contents of any magic square do not have to be our favorite consecutive positive whole numbers 1, 2, 3, 4, 5, and so on. In theory and in general, it is possible to fill out any magic square with the elements of one and the same arithmetic progression, as long as the difference between the adjacent elements is one and the same. But using this other arithmetic progressions in order to fill out the contents of any magic square does not bring anything new fundamentally or essentially. That is why, in some sense, the simplest arithmetic progression, our favorite consecutive whole positive numbers, 1, 2, 3, 4, 5, 6, 7, is enough. with that out of the way, what is the constant of a magic square? The constant of every magic square is one and the same, evidently whole positive number, to which all the numbers in each row, in each column, and in each of two, the main and the secondary diagonals of the magic square at hand, sum. And how can we compute that constant if we know, for example, that we will fill out our magic square with consecutive whole positive numbers 1, 2, 3, 4, 5, and so on? Well, let's say if we record the sum of all the numbers in all three rows of our 3 by 3 magic square, what will these sums be? Well, on the one hand, this will be the sum s for the first row plus the sum s for the second row plus the sum s for the third row. And if we sum all these numbers, how many sums will we get? We will get precisely 3 sums. That's on the one hand. On the other hand, if we sum all the numbers in all 3 rows, what we will do? We will hash the numbers 1, 2, 3, 4, 5, 6, 7, and so on somehow, but whole positive numbers commute under addition, which means that for any 2 whole positive numbers, a plus b is the same thing as b plus a. Consequently, we can stretch our hashed and mixed in some wild ways the numbers that fill out this square in their natural order. And what will we obtain? We obtain our favorite sum of consecutive whole positive numbers from 1 to 9. That sum will be what? 9 times 9 plus 1 over 2. We remember that much. So this is what? 9 plus 1 is 10. 10 over 2 is 5. 5 times 9 is 45. 45 over 3 is what? 15. Wonderful. So S, the constant of our square, is 15. Now that we understand where does the sum of our magic square come from, we can begin our elimination rounds. And according to the eliminate and conquer problem solving approach, if we want to apply that approach to the process of generating a solution of this or that technical problem, our first step is to somehow identify the pool of all the suspects. In this case, what is the initial or starting point for filling out a 3 by 3 magic square? What is the pool of suspects? Well, one way to approach the process of filling out a 3 by 3 magic square using the eliminate and conquer problem solving approach is to reason from the largest possible number in the set. And what is the largest possible number in the set? In this case, the largest possible number in the set will be what? Precisely, that will be number 9. So the pool of suspects in this case will be actually the possible locations of the largest number in the set with which we will fill out a magic 3 by 3 square. Consequently, we want to look at the worst possible cases first and see if we can eliminate them somehow. And then the hope and the idea is that when we eliminate all the impossible or the worst case scenario locations for the largest number 9, what will be left is the truth, so to speak, the proverbial truth, or the possible locations for the number 9 to dwell in. And in our first elimination round, we will begin with the central square. Remember that when the order of a magic square is a number that is odd, in season 2, episode 29, we also showed that in such a square, there always exists a so-called central cell. That is not too difficult to see because the number is odd. For example, let's say the odd number 2n plus 1 can always be partitioned which way? Well, n plus 1 plus n, and bingo. The monkey in the middle is precisely either way. Rows, columns, and their intersection gives us the central cell. In season 2, episode 29, we also proved that when the order of a magic square is a number that is odd, the contents of the central cell are not for grabs. They're not up for discussion. The contents of the central cell in each and every magic square whose order is odd is fixed. And we proved in this episode that that number must be s divided by n, or the constant of the magic square divided by its order. In our case, that number will be what? 15 over 3. So the contents of this cell must be 5. We know that much, but it is a good idea to pronounce or to say out loud why the number 9 positioned in the central cell cannot possibly happen. Well, let us do that right now. If the number 9, the largest number in this set, is positioned in the central cell of a 3 by 3 magic square, then what does that mean? That means that this number will participate in how many sums? Well, it will participate in the vertical sum of the central column. It will participate in the horizontal sum of the central row, and it will participate in the sums that are both diagonals. And what else can we say about the largest number 9? Well, the largest number 9, let's see, let's think about this carefully. Is this number somehow compatible with the numbers 8, 7, and 6? I'll list these numbers in the descending order. Well, 9 and 8 is already 17, and 17 is greater than 15. This is a no starter right away. 9 and 7 is 16, and 16 is greater than 15 again. This is not a starter. 9 and 6 is 15, but we still have one cell to account for, so no matter which whole positive number we add to the sum of 9 and 6, we already step over the number 15 right away, so this is not a starter. What about number 5? Well, 9 and 5 is 14, and that means that there is hope. The number 5 and the smaller numbers do not make it into this pool of incompatible numbers. And what does this observation mean over here? Well, this observation means that, bringing in a little bit of physics, imagining that number 9 is a charged particle, that means that the particles with the like charge repel. So this means that the charged particle number named 9 must have the same charge with the particles named 8, 7, and 6. They must repel, or geometrically that means that spatially they must be separated enough so that they never enter into one and the same sum. But if the number 9 is located in the center cell of a 3 by 3 magic square, can that constraint be honored? The answer is obviously not. No matter where we put numbers 8, 7, and 6, they will always enter into the sum with the number 9. Thus, we conclude that the number 9 cannot possibly be in the central cell of a 3 by 3 magic square. And in the next segment, we will consider which possible other location. Well, we'll carefully move the number 9 from the central cell into one of the corner cells, and we will do that in the next segment. Wonderful. Now that we carried out one round of elimination and we proved that the largest number in the set, 9, cannot possibly be located in the central cell of a 3 by 3 magic square, now we carefully move the largest number in the set, 9, away from the center cell into one of the corner cells. And due to the symmetry of the given shape, and the theory of groups, in a few minutes we'll have something to say about that symmetry, we can consider for our analysis the location of the largest number in the set, 9, in any of the corners of the square. It doesn't matter which one. We pick one, let's say this one, upper left corner. We place 9 for our simple reasoning over here, but you can place 9 here, here, or here. It doesn't really matter. The fundamental essence of this analysis will not change. Now, if we place the number 9, the largest number in the set, in the upper left corner of our square, then what does that mean? Well, in this case, let us see. The number 9 will participate in how many sums? In the previous segment, we showed that if the number 9 is positioned in the central cell, then it participates in how many? 1, 2, 3, 4. Four sums. And if we place the number 9 in the corner of a square, then that number will participate in how many sums? The vertical sum over here of the leftmost column, 1. The horizontal sum of the topmost row, 2. And then what else? And in this case, the main diagonal. So now we reduce the number of sums in which the largest number in the set participates from 4 to 3. So things beginning to look up a little bit, and bringing the wonderful game of chess into our discussion. What does this location of the number 9 mean? Well, remember the chess knight. It moves in the L-shaped configurations. This cell, in this case, with respect to 9 located here, we have this cell, and what other cell? Down and right. And this cell, remember in the previous segment we talked about sufficiently spatially divorced or separated the number 9 from the numbers 8, 7, and 6. These two cells, in this case, this cell and this cell of our 3x3 magic square is what? Is sufficiently separated spatially from the usual suspect 9. Would you agree? If we place a number in this cell or in this cell, then we hide the numbers in these cells from participation in the sum with the number 9. However, how many such cells do we have in this case? Only 2. And how many incompatible suspects do we have with number 9? 3. 3 is greater than 2, so that still means that we have absolutely no hope of making things work and summing our numbers to 15, because if we hide any two numbers from this set, let's say we place 8 over here and 7 over here, then no matter else we place the remaining number 6 here, 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 or here, then number 9 will collide with number 6, produce the sum of 15, and another square that will be left over will bring the sum of the numbers with 9 and 6 what? Over the top, and violate the constraint that the constant of the square must be 15. Likewise, if we place, for example, numbers 7 and 6 in the hidden cells, then the number 8, no matter where we place it, will enter into the sum with 9 and bring it over the top. And this is also an important observation, that when we hide the numbers, for example, in this cell and this cell, the remaining number must be placed somewhere in the square. It cannot not be placed in the square. And this analysis also does what? It eliminates any of the corner positions for the largest number in this set. None of the corner positions are acceptable for housing the largest number in this set. Thus, what do we have left? Well, essentially we have only 4 squares left. The central cell in the top row, the central cell in the bottom row, the central cell in the leftmost column, and the central cell for the rightmost column. But again, because our shape at hand is highly symmetrical, which one of these legal, so to speak, or hopeful cells for housing number 9 we pick does not matter. We will do that in the next segment. In the episode in which we explained how the eliminate and conquer problem-solving approach works for the first time, we observed that the eliminate and conquer problem-solving approach does not really good candidate for winning any medals for elegance and exquisiteness. In other words, the method of exhaustive enumeration does not really shine and sparkle with intellectual voltage. But on the other hand, when it works, it works. And that means that in the previous 2 segments, we generated a valid mathematical proof that the location of the largest number in the set, 9, cannot possibly be the central square of a 3 by 3 magic square and none of the corner cells of our 3 by 3 magic square. That elimination puts us into which position? That elimination puts us into the position to only consider the 4 cells that we mentioned in the previous segment: the central cell of the top row, the central cell of the bottom row, the central cell of the leftmost column, and the central cell of the rightmost column. Due to the symmetry of the square, which such cell to house the largest number in the set 9 we pick does not really matter. For experimentation purposes and for demonstration, let's say pick, let me put the red, use red chalk. I'll put number 9 in the top row, in the dead center of that row. Now what do we do next? Next we bring in the fact that when the order of a magic square is a number that is odd, then the contents of its central square are not up for discussion. These contents are locked in, and they must be the constant of the magic square divided by its order. In our case, the constant of the square is 15, the order is 3, 15 over 3 is 5. So we already proved mathematically that the contents of the central square must be what? Let me probably use another color just to make sure that we underscore the importance of this. The contents of the central square must be 5. And now our favorite eliminate and conquer problem solving approach is laughing all the way to the bank, because what remains to do now is just to unleash the eliminate and conquer problem solving approach onto this configuration and experience the eliminate and conquer bonanza, so to speak. What is the possible, now that we have the contents of the top 2 cells in the central column filled out, what does that mean? Well, in general, from the group theoretic, from the number theoretic perspective, when the numbers are large, yes, we may have different possible combinations of different ways to put different one and the same number together. But in this case, the choices are pretty much, all the other choices are eliminated. 9 and 5 is 15. 15 minus 1 is 9. 9 and 5 is 14. 15 minus 14 is 1. So the contents of the bottom cell, in this case in the central column, is locked in. It's 1. Now we go back to our numbers, and this is where the number theoretic flavor comes in a little bit. The remaining, we know that here, with the number 1 participating in the horizontal sum of the bottom row, we have only 2 choices. So our constant of the square is 15. 15 minus 1 is 14. So in how many ways we can generate 14 as a sum of 2 whole positive numbers? Well, 9 and 5 was one way. And what is the other way? Well, in this case, we need to be careful. The only other way is what? Is 8 and 6. Again, where we put 8 and where we put 6, it doesn't matter. We can put 8 over here, 6 over here, or we can put 8 over here and 6 over here. I'll put 8 in the lower left corner, and just for experimentation purposes, I suggest that you guys do some pick some other location. Put, for example, 8 over here. So we put 8 in the lower left corner. We put 6 in the lower right corner. What is next? By doing this, we also eliminate a lot of choices or a lot of possibilities for the contents of which square, which cells in our magic square. This cell and this cell. Again, 8 and 5 is what? 13. 15 minus 13 is 2. Boom, we have the contents of the upper right cell. It's 2. 2. This one is 6. Let me make it thicker so you guys can see it better. And this is 8. Wonderful. Now that we know that 6 and 5 is 11, 15 minus 11 is what? 4. So the contents of this upper left cell is also locked in. 4. As a double check, 4 and 9 is 13. 13 and 2 is 15. And now we're squeezing our eliminate and conquer vice, so to speak, tighter and tighter and tighter. And what do we have left? Only 2 choices. The center cell of the leftmost column and the center cell of the rightmost column. And the contents of these cells are also locked in pretty much. 8 and 4 is 12. 15 minus 12 is 3. So we enter 3, and for the central cell of the rightmost column, what do we have? 6 and 2 is 8. 15 minus 8 is 7. And voila, we have our magic square, or do we? This is an interesting question. Once we fill out our 3 by 3 magic square in this particular way, for example, and we have a magic square, the interesting question is this configuration it, or we can say something else about possible flavors of the 3 by 3 magic square that we just constructed. Now, you don't have to know anything about the theory of groups altogether to answer this question in the negative. No, we're not done yet. But it pays to know a little bit of geometry and realize that the figure or the shape at hand, called the square, is quite reasonably symmetric. And in the next segment, we will investigate why the answer to the question, are we done with this magic square? Yes or no is no. Before we understand why the answer to the question, are we done with the magic square that we just constructed, or no, is in the negative, no, we're not done yet. We have more work to do. Here is a 30 seconds or less crash course introduction into the theory of groups, but do not worry, it will not be difficult. We will not be computing automorphism groups yet. But let's imagine that we take our favorite square and we make 2 copies of it. One copy we will call a workbench or a table copy, and in the language of physics, this will be our stationary reference copy. It will remain stationary and fixed at all times. The second copy of a square will be a traveling copy, and it will be moving or traveling with respect to the stationary reference frame square. And it turns out that mathematicians have noticed that a square, being a regular polygon, possesses small number of non-trivial transformations that take that square back into coincidence with itself. For example, one such transformation, called a congruence motion, is the rotation of the traveling or rotation of the parent square about its center, O, in the parent plane, counterclockwise by, let's say, pi over 2 radians, like so. This is the initial position. This is the final position. And in the final position, note well that the traveling copy of a square completely coincides with the stationary reference frame square. You see, this is the initial state. During the motion, it is important to understand that during the congruence motion, it may very well so happen that the traveling copy of a square will not coincide with the stationary reference frame copy, and that is fine. The only thing that matters when it comes to the congruence motions of regular polygons or congruence motions of geometric figures and shapes in general is the final state. In the final state, if we name our vertices of the square as 1, 2, 3, and 4, then we will notice that after the rotation of the parent square in the parent plane about its center by pi over 2 radians counterclockwise, for example, the vertex of the square that used to be 1 now is taken into the vertex of the square that is named 2. 2 is taken into 3. 3 is taken into 4, and 4 into 1, and thus enters the picture the wonderful theory of combinations, but permutations. But the interesting question for us right now is this rotation the only way to bring a square into coincidence with itself? And the answer to that question is no. We can bring a square into coincidence with itself with 2 more rotations by pi radians counterclockwise about its center in the parent plane, and by 3 pi over 2 radians counterclockwise in the parent plane about its center. In addition, it is also possible to bring our square into coincidence with itself with 4 reflections in its 4 axes of symmetry. It should be evident that a square possesses precisely 4 axes of symmetry, 2, let's say, medial axes of symmetry that connect the dead middles of the opposite sides, the top and the bottom and the left and the right, and 2 diagonal axes of symmetry. Consequently, if we take, for example, our traveling copy, making sure that it coincides with the stationary reference frame copy, and then we flip or reflect the square in its logically vertical axis of symmetry like so, this way, you see, this way, then what will happen? Again, the square will be brought into coincidence with itself. Consequently, a reflection of a square in its axis of symmetry is also a congruence motion. Reflection of the square with respect to its medial axis of symmetry, or here is, for example, the reflection of the square with respect to one of its diagonal axes of symmetry. See, this is how it works. And it turns out that these are the only congruence motions that a square possesses. And it so happens that in the theory of groups, it is shown that such congruence motions of a square under the operation of composition, meaning one operation is followed by another, forms a group that is isomorphic to the finite dihedral group D4, shown over here. The symbol D stands for dihedral, the index 4. Basically, if we agree that such groups are generated by, for example, regular polygons, then it will show us the index in the dihedral group designation will show us how many sides does the generating polygon have. And the cardinality, or the size, because this group is finite, the size of this group is precisely 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. And the element symbolized with E stands for the identity element, or in this case, the identity transformation when the square is not acted upon at all, or if a square, for example, acted upon in such a way that the final motion, for example, brings it back into coincidence with itself with the original state. If we rotate the square about its center in the parent plane counterclockwise by what? 2 pi radians, this is exactly the identity transformation. Now, the symbols R over here, R, and R stands for rotation. The subscript next to the letter R shows the center with respect to which the rotation is carried out, and the superscript shows the angular measure with respect to which the rotation is carried out. There is an implicit plus sign over here, and the positive direction in mathematics is taken by default counterclockwise. The letters S in the designation of the elements of the dihedral group stands for symmetry, and the subscript of that symbol tells us with respect to which geometric object the symmetry is deformed. In this case, the symmetry is carried out with respect to the 4 axes of symmetry named M1, M2, D1, and D2 for 4 reflections, 3 rotations, and 1 identity transformation. 4 plus 3 plus 1 is 8. This is the size of the dihedral group D8. And in the square that we just constructed, I designated with yellow color, with yellow chalk, the vertical medial axis of symmetry of the square named A1, and the horizontal axis of symmetry, also medial, because it connects precisely the middles of the opposite sides of the square with the letter M2. M1, M2. Here, these guys are again M1, M2. This is basically the way this should be read is the following. The reflection of the parent square with respect to the axis of symmetry M1, M2. There, the reflection of the square with respect to the diagonal axis of symmetry. Over here, I showed the axis of symmetry that are diagonal in green, this one, D1, and this one, D2. Now we will conduct the following experiment. Whatever magic square we constructed, and remember when we were trying to find the home for number 9, we had some variance. We could have placed it in this square, or that square. For example, I decided to place it over here for demonstration purposes. That's fine. You could have picked a different location. Also recall that we had some degree of freedom of placing the numbers 8 and then 6. For example, I placed the number 8 in the lower left corner and the number 6 in the lower right corner. I suggested that you place it in different locations, and an interesting and mathematically hefty question is the following. If you were to place the numbers 8 and 6 in a different way, would that placement result in a different square than the one is shown over here? As such, the question is, if we take the square that we constructed and correlate it with the identity element of the dihedral group D4, then what other good things can happen over here? Well, if we correlate to each non-trivial element of the dihedral group D4, rotation about the center in the parent plane by pi over 2, pi and 3 pi over 2 radians, and the reflections of the parent square in the corresponding axis of symmetry, we will automatically and mechanically, pretty much with very little thought, obtain 7 more copies. 1, 2, 3, 4, 5, 6, 7. 7 more copies of our parent or generating 3x3 magic square. And before we move on and try to discuss or understand or wrap our brain around the question, okay, will the resultant squares be the same or different? Let us carry out a couple of these transformations. Let's say I will do one of each. I'll do one rotation about the center of the square by pi over 2 radians, reflection in one in the medial axis of symmetry and one reflection then in the diagonal axis of symmetry of a square. And I suggest that you guys carry out all the other ones so that you get the feel for what is going on. Now, before we jump and deep dive into our manipulations, let's think about it. Remember, the contents of the central square of any magic square of an odd order is not up for discussion. This content is fixed. So number 5 is placed right away automatically without much thought into every central cell of our future magic square. And also, one of the absolutely wonderful things about mathematics is, in this case, look at this. The theory of groups, the underlying geometry, and the underlying miniature theory of magic squares all agree on the location of the number 5 in this case, or on the contents of the central cell. Why is that? Because no matter how many times and by what angular measure we rotate the square, the center of the square will always remain what? Fixed. And in this case, when the order of the magic square is odd, the role of the center of the square can be placed precisely by the center cell. And reflections of the square in any of its axes of symmetry will also leave the center cell intact or in place, or as they say, fixed. So now let us together carry out this transformation over here. Let's rotate the parent magic square that we constructed in the previous segments about its center in the parent plane counterclockwise by pi over 2 radians. This angular measure right here, this will be the square, and this square will correspond, there's a little bijection if you will, correspond to this element of the dihedral group, the rotation about the center by pi over 2 radians counterclockwise in the parent plane. Let's start with the number 2. The angle between the diagonal axis of symmetry of any square is what? 90 degrees. Consequently, if we rotate the square by 90 degrees, the square number 2 will jump over here in the corner where number 4 used to be. The number 9 will flip 90 degrees into where 3 used to be, 9. What about number 4? Number 4 will do a 90-degree jump over here. This will be 4. Number 3 will jump 90 degrees to where number 1 used to be, number 3. Number 8 will jump 90 degrees to the number 6 corner. 8. Number 1 will jump where 7 used to be. 1. What about 6? 6 will execute a 90-degree jump into where 2 used to be. This is 6. And finally, closing the circle, so to speak, the number 7 will jump where 9 used to live. So this is number 7. And this is it. So this square correlates to this element of the dihedral group D4, the group of all rigid symmetries of a square, and this element corresponds to this square. Now let us move on. Let me use the yellow chalk. Let me execute this element of the dihedral group D4, the group of rigid symmetries of a square. I will put the arrow here. This element corresponds to this square, and this square corresponds back to this element, which is what? Is a reflection of the parent square in the medial axis of symmetry, that in this case, the way we see and the way we look at the square connects the opposite middles of the top and the bottom sides. It stands to reason that if we are reflecting our square with respect to the central, to the vertical, this axis of symmetry, again, in the squares of odd order, the central column will always exist. It will remain intact or fixed under the reflection of the square along this axis of symmetry right here, vertical one. So here we can fill out the numbers right away. So 9 will stay on the top, and 1 will stay on the bottom over here. 9, 5, 1, 9, 5, 1. Now what will happen to the numbers, let's say 2 and 4? Well, under the reflection with respect to the vertical axis of symmetry and 1, the numbers 2 and 4 will trade places. You see, number 2 will jump over here, number 4 will jump over here. The numbers 3 and 7 will trade places under this reflection, so 7 will live over here, 3 will live over here. Likewise, the numbers 6 and 8 will trade places with respect to the vertical axis of symmetry M1. So now 6 goes here and 8 goes here, and we're done with the reflection of the square with respect to the medial axis of symmetry, to which we refer as M1. Lastly, just for variety, let's reflect our square in the diagonal axis of symmetry D1. So this square that we will generate will correspond to this element of the group of rigid symmetries of a square D1, SD1, and SD1 will correspond to this square. Let us carefully do this reflection together. If we reflect our square with respect to the axis of symmetry called D1, that means that the diagonal, all the squares that live on that diagonal, let's call them main diagonal, will remain fixed or immovable. They will not move anywhere. So numbers, what is this? 4, 5, and 6 will remain where they are. 4, 5, and 6 will be where they are. Now, let's look at the numbers 1 and 7. With respect to this diagonal, numbers 1 and 7 will trade places. You see, 1 and 7. So 7 will jump over here, and then 1 will jump over here. Now let's move on. Numbers 8 and 2. See, under the reflection, they will trade places. Under the reflection with respect to the diagonal D1. 8 and 2. So 2 goes here, and 8 goes here. Wonderful. Lastly, what do we have? 3 and 9. With respect to the diagonal D1, number 3 will jump where number 9 used to live. Number 9 will jump where number 3 used to live. So number 9 goes in red. So it makes it easier for you guys to keep track of what is going on. And we are done. So just to make sure that it's easier for you to keep track, this square, let's say we'll call it M1, reflection in M1. This square is a reflection in D1. Reflection in D1. So far, so good. Now comes a very deep, meaningful, interesting, and mathematically hefty question. What do you guys think? These extra 3 squares that we just constructed, by basically carrying out the blueprint that is baked into the heart and soul of the dihedral group D4. Are they different from the parent square, magic square that we constructed in the previous segments or not? Here the answer is the following. Again, we suggest that you put this video on pause, walk away from the computer, think about it, then come back and compare your ideas with ours. The answer to this question comes in two directions. One, if we decide to assign named cells to our square, for example, the cell named A11 for row 1, column 1, A12, A13, A21, A22, A23, A31, A32, A33, all cells have their own specific name. Then the answer to our previous question is yes, technically the squares will be different because, for example, the cell named A11 carries the value of 4 in our parent square, and what value does it carry after it was rotated? The value number 2. 2 is not 4, 4 is not 2. Boom, at least one this difference. The squares must be different. That's what we have to admit. But on the other hand, the mathematicians will perhaps borrow the terminology from the theory of groups, and they will say that the copies, these 3 extra copies that we constructed together, and all 7 copies that you guys constructed on paper on your own, are basically the isomorphic images of the parent square. That means that these extra 7 copies are essentially the same. What does essentially the same mean? Well, in terms of the theory of groups, for example, essentially the same means that the elements of the group can be of different nature, and the operation that acts on these elements, the group operation, may have different natures too. But if we ignore these details, the structure is the same, then we say that the groups are essentially the same or isomorphic. In this case, we will also say that if we're willing to ignore the fact that the named cells carry different values, if we ignore this fact, then the copies of the squares that we produced according to the blueprint baked into the dihedral group D4 are essentially the same or isomorphic or basically the same. How can we see that? Well, let's concentrate, pick any number. I don't know, pick number 2, for example, again. From the standpoint of its immediate neighbors, what can we say? In our parent magic square, the immediate neighbors of the number 2 are what? 7, 5, and 9. Would you agree? 9, 5, 7, 7, 5, 9. There are no other immediate neighbors that the number 2 has. What about the same thing, the same analysis in all the other and seemingly different squares? Well, let's take a look. Number 2 has which immediate neighbors? Again, 7, 5, 9, 9, 5, 7. No extra neighbor managed to creep in. 3 is not an immediate neighbor of 2. What about this square, the one that we reflected in the vertical axis of symmetry, with respect to the square that carries the value of 2? 9, 5, 7. 7, 5, 9. Still the same 3 numbers. What about this square right here? Where is number 2? Here. What are the immediate neighbors of the square that carries the value number 2? 7, 5, 9, 9, 5, 7. Bingo. No matter where we go, the number 2 has one and the same set of immediate neighbors, 9, 5, and 7, if, of course, we ignore again this idea of assigned cells. And the claim is, if you guys will construct the remaining 4 copies of isomorphic copies of our magic square, the same scenario will hold. Number 2 will have the same immediate neighbors, 7, 5, and 9, in all 8 copies of, in all, let's say, 7 copies of the parent square. And the statement will also hold true for all the other numbers. Let's say we pick, I don't know, pick number 3, for example. 3. What are the immediate neighbors of number 3? 4, 9, 5, 1, 8. This guy sits in the middle of the middle row over here. 4, 9, 5, 1, 8. Let's find number 3 somewhere else. 3 right here. So what do we have? 4, 9, 5, 1, 8. 2, 7, 6 never squeeze their way into or muscle their way into number 3, to being an immediate neighbor of number 3. What about here? 49518. What about this one? What is this? 49518. This is the bracket for number 3. You see, this scenario will hold for all the numbers in the parent square, and thus we have it on the one hand, technically, yes, the 7 extra copies are different, but if we are willing to ignore certain details, such as assigned cell names, then the theory of groups has a good buck on the fact that these 7 extra copies are the isomorphic images of the parent square, or basically means that they are essentially the same as the parent square, whatever it is. What does this observation tell us? This observation tells us that if somehow we can figure out all possible magic squares for a given order, that number must be what? I can't hear you. Yes, that number must be divisible by 8. You see, that number must be divisible by 8. Why? Because for every genuine copy of a magic square, 7 isomorphic copies of it come in mechanically, courtesy to the theory of groups in general and the dihedral group D4 in particular, by carrying out the 3 rotations and 4 reflections as we explained. And what does that mean? That means, let's say we have a huge pile of magic squares of order 3. We pull the square out of the pile, we pull the other one, and we see, can one square be produced from this square from another square by carrying out any of these 4 congruence motions, 3 rotations, either one of 3 rotations or either one of 4 reflections? If yes, we kind of carefully have to put it aside because this isomorphic image is not it. We keep 1. And this way, by the time we eliminate all the isomorphic copies of whatever we picked, we will get a set of genuine, so to speak, unique squares of magic squares of the given order. We're almost done with this segment. One more thing for the brighter individuals in our community. I have another informal homework assignment for you guys. Think about this. Let's say you constructed a magic square, 3 by 3, 4 by 4, 5 by 5, it doesn't really matter. Let's say 3 by 3. And now you want to send to your grandmother Morse code or smoke signals, whatever, the pigeons as some sort of signals. Here is the challenge. Design a protocol that uses nothing but, let's say, good old ASCII symbols, let's say printable ASCII symbols, that tells a story without the loss of information about this unique magic square. In other words, if you put your sequence of symbols on the communication line, your grandmother takes them off the line, she assembles somehow the magic square, boom, and the 2 magic squares, the one that you constructed and the one that your grandmother constructed, bam, they're exactly the same and they are identical. In other words, let's say in your protocol, you have to say something like, the first position will be designated for the size of the square, 3. And this is it. Then semicolon, another ASCII character. And then number 2 has immediate neighbors, somehow designate neighbors. What is this? 9, 5, and 7. 9, 5, 5, 7, and 9, and so on. Basically, again, a string of ASCII symbols that can be put on the communication line, 1 character at a time. Someone can read it off that line and reconstruct your magic square without loss of any type of information with absolute certainty, and so to make sure that that copy is the same. This segment is optional. It is for curious travelers only. If you're not interested in what we have to say about the theory of groups, then feel free to fast forward to the next challenge. Meanwhile, in this segment, we will show how the eliminate and conquer problem solving approach can be applied in a grown-up, albeit admittedly rudimentary, group theoretic setting. That is, let us assume for a moment that we're given a group G with 3 elements, E, A, B, and that is a set that is equipped with a single associative and binary operation. And in the theory of groups, there exist at least two distinct ways to visualize what a group is. One such way is a graph of a group, and the other such way is a multiplication table of a group. And we constructed the carcass for such a multiplication table of a group over here. And as you can see, it resembles the 3x3 magic square that we dealt with in the previous segments. And the question now is, if we are to capture the specific way in which the elements of this group G interact with each other via the group operation designated with a small circle, then how many such groups, how many such different, perhaps, groups of order 3 are there, which translates into how many essentially different multiplication tables of a group G of order 3 exist. And again, we will answer that question precisely by using the eliminate and conquer problem solving approach as follows. When we construct a multiplication table of a group, there exist certain conventions or agreements, and these agreements and conventions are arbitrary. These things can be done in a number of different ways, but for the most part, the mathematicians over the years have agreed to write down the elements of the group in the top row that plays the role of the column headers, and to write down the elements of the group pretty much in the same order in the leftmost column, whose entries represent the row headers. And again, this is a convention. It is quite popular that in the way in which the elements of a group interact with each other, that way is captured as follows. Whatever sits in the column header goes on the right, and whatever sits in the row header goes on the left of the product. In other words, in this cell over here, upper left cell of our 3x3 table, that contains how many cells? 3x3, 3 squared, 9, precisely as many cells as we had in the magic square in the previous segments. And in each such cell, we record the result of the interaction between two group elements. This is precisely, in some sense, what does it mean for the group operation to be binary? That means that when any two elements of this group interact with each other via the group operation, the result, this group operation, must return not some wild element, but precisely one of the elements of the set G. As such, in every cell, we are to recover the contents of each cell, which contains the result of a group theoretic product. For example, E is the so-called unique double-sided identity of a group, which is an element such that when we multiply any other group element by E, we obtain the group element that we multiplied E with. Consequently, in upper left cell of our 3x3 multiplication table of this group, what entry will go here? E on the left, E on the right. Let's say I'll write it down right for you over here. E on the left, E on the right. This produces E. So consequently, the element named E, where's my yellow chalk? The element E goes into this cell. The next cell, A goes on the right, E goes on the left. I'll write it down, guys, for you over here. E on the left, A on the right. What is the result of this product? A, the group element A. We'll write it down in blue. Same way, what will be the contents of the upper rightmost cell? E on the left, B on the right, connected with the group product like so. Let me write it down over here for you. E times B will be B. So here we write the element B right away without thinking much about it. And the same goes for the column. When we multiply E element A by the identity element E from the right, we obtain the element A, and the same goes for B. B times E from the right equals to B. So that much we can fill out. The 5 cells out of 9 can be filled out automatically, quickly, quite mechanically, but the contents of the 4 cells shown over here in the lower right corner, Now, this is where the eliminate and conquer problem solving approach shines. This is where we unleash the eliminate and conquer problem solving approach on these 4 cells. And here again, how do we lasso in all the possible suspects? Well, remember that the product of any 2 group elements has to be another group element. Let's work on this cell right here. What can be, what kind of element can possibly live in that cell? In that cell, there lives the product A times B, and our lassoing will have to include what? The identity element, the element A, and the element B. This is all possible. This is our pool of suspects. As such, for example, let us contemplate. Can A times B be, for example, A? What happens if A times B is equal to A? Can this situation occur? This is our elimination rounds. You see, if we multiply this equality by the inverse of A, denoted with A to the minus first power, from the left, then we will have A to the minus first, A times B is equal to A to the minus first A. This is exactly where we'll reuse the fact that the group operation is associative. We'll first combine these 2 elements. These 2 elements produce E times B equals to, again, E. And then what does that mean? That means that the element B is equal to element E. But this is absurd. This is a contradiction. Every element of a group is unique. This is impossible. Consequently, the product of A and B cannot possibly be A. No good. Does not work. Eliminate it. By the same token, can this product be equal to B? Well, it's not difficult to see. We'll execute the same maneuver, but this time we will multiply this equality by what? By the inverse of B from the right. And then we will have identity A equal to E. Is that possible? No, it is not possible. This is absurd. This is a contradiction. Every element in the group is unique or distinct. This is not possible. Now we go back to our favorite Sherlock Holmes, when everything that is impossible has been eliminated. Whatever remains, no matter how improbable, is the truth. Consequently, the only choice for the product of the elements A and B must be what? Must be E. So this element, this cell, is filled out. By exactly the same maneuvering, we can establish what? That the product between the elements B and A. Here, this product will look which way? Here it was A times B, but in a separate, we will do what? B times A. And again, if we try to equate it to B, or if we try to equate this result of this product to A, we'll derive a contradiction that either A or B must be the identity element. This is absurd. This cannot happen. Every element in the group is distinct. This is not possible, so the only choice is the identity element. There we go, the identity element E. Now that we established that, let's write it down. A times B is equal to E, and B times A is equal to E. What are the possible values? Let's try to fill out these 2 cells. What are the possible results that will go into this cell where A times A is the product? What can this product be equal to? What are the choices? Well, precisely because we established that A times B equals to A, if we assume that A times A is E, then what does it mean? It means that B is equal to A, but this is absurd. B is not equal to A. Every element in the group is distinct. Consequently, A times A cannot possibly be E. Does not work. Do you feel another contradiction coming up? If we equate this to A, what would that mean? If we multiply this equality through by A from any side, by the inverse of A from any side, what will we have? We'll have again that A is equal to E. Absurd. This is not possible. Consequently, the only choice now that E and A have been eliminated is what? Precisely, it can only be the element B. Likewise, if we conduct the same experiment, if we write down product what? B times B is equal to. Can it be equal to, can this product be equal to E? No, it cannot. Remember, B times A is E. That means that this will imply that B is equal to A, but this is absurd, a contradiction. Every element in the group is unique. So E is out, eliminated. Can this product be equal to B? We keep continuing, we keep carrying out the, remember, keep eliminating the impossible for as long as possible. We keep doing that. Can this product be equal to B? Evidently no. If we multiply this equality by the inverse of B, from either right or left, it doesn't matter, we will deduce another contradiction, that B is equal to E. This is also impossible. So what is the only choice? E is eliminated, B is eliminated. What is the only choice? A, correct. A is the only choice. You see, this is how the eliminate and conquer problem solving approach slays, so to speak, admittedly rudimentary, but still a legitimate group theoretic problem of investigating of how many different copies of multiplication table of the group on 3 element exists. Of course, if we agree that we need to align the elements that way up to this order, there actually only one multiplication group and only one group of order 3. Why? Because in our deduction, we did not make any special assumptions about the nature of the element and did not make any special assumptions about the nature of the operation that glues these elements together. And of course, later on in the theory of groups, we'll learn that the order of this group is 3. This is a number that is prime. It has its own significance, but nonetheless, for demonstration purposes, this is precisely how we will establish the fact that there is essentially or fundamentally one and only one multiplication table of a group of 3 elements. Now, this is it for the mathematical problem S2M36, and we will move on to a new challenge next. In our next challenge, the mathematical problem S2M37, we're given a regular polygon on n vertices, and let us pretend, for demonstration purposes, to establish a common ground, that the names of the vertices of this regular polygon are A1, A2, A3, and so on, AN, where n is a strictly positive whole number, and that polygon has the following properties. The reciprocal of the distance between the vertex of this polygon named A1 and the vertex of that polygon named A2, the distance, is representable as the sum of the reciprocal distances between the vertex, again A1, but this time A3, and the distance from the vertex A1 again, yet again, and A4 this time, and A4. So when we have a regular polygon on n vertices with this specific property, the question is, what is the value of n? In other words, is this an equilateral triangle, a square, a pentagon, a hexagon, a regular pentagon, a regular hexagon? What type of a regular polygon is it? Try your hand at solving this problem, and again, as a hint, we are using the eliminate and conquer problem solving approach. Right now we're studying this problem solving approach in a dedicated manner, so it stands to reason that just because of the placement of this problem, it may be a good idea to try to apply the eliminate and conquer problem solving approach to the process of recovering the answer. And again, remember that mathematics is an art of telling a story of how and why, and in the big scope of things, no one in the mathematical community cares about the value of n, but everyone in the mathematical community cares about your ability to generate an interesting and convincing story of why the value of n, in this case, what it is. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M37.